Welcome to Pre-Calculus. Today we will investigate solving polynomial equations, focusing on how using different strategies such as factoring or use of the quadratic formula identify different sorts of solutions for any given equation. We'll take a look at two examples. And the first that we're looking at is a cubic equation. So this one says solve the polynomial equation by factoring. And that's typically a good first attempt in terms of a strategy to find solutions to a polynomial equation. We do have a second step for unfactorable quadratics. Use the quadratic formula to find irrational or imaginary roots. And then once we've got our solutions, we want to label any multiplicities. So let's start off with this x cubed plus 6x squared plus 8x equals 0. So one thing to be on the lookout for is how many of the terms in your equation involve the variable x, in this case the variable x. So I'm just going to go through and highlight my x terms here in each of these terms. So I've got an x to the power of 3. I've got an x to the power of 2, and I've got an x, which I'll assume to be to the power of 1. Now, if I've got an x variable in each term in the polynomial, that means that I can directly factor out the lowest power of x. So kind of our limiting factor there is x to the power of 1. So my first step, I'm going to factor out x to the power of 1 and then see what's left in terms of the factors once I pulled that x out. So it's really division. So when I'm factoring out an x, I'm really saying what's x to the power of 3 divided by x to the power of 1. And you can recall that to simplify that quotient, I would subtract the exponent. So 3 minus 1 is 2. So that'd leave x to the power of 2 plus 6x. If I divide that by x to the power of 1, 2 minus 1 is just 1. So 6x to the power of 1. And then if I divide 8x by x, that just leaves 8. So what I see that I've got now within the parentheses here, if I highlight in green, is a quadratic factor, x squared plus 6x plus 8. And anytime I have a quadratic factor, I want to try to factor that into its linear terms. So a good way to set that up is just by using this x factor, and it's a way of guiding our questions about how the linear factors are going to look. So I'll create them there. We'll have x plus something and then x plus something. What we got to discover are those numbers. So this setup helps. The way we use the x factor is we put our c term. So if I'm thinking about a quadratic, it's ax squared plus bx plus c. My c term's that constant. So I want to look for two numbers that multiply to give 8. But then add up to my b term. My b term here is 6. So two numbers that both multiply to 8 and add up to 6. So let's think for a moment. 1 times 8 multiplies to 8, but 1 plus 8 is 9, so that doesn't work. I'm looking for them to add to 6. So then I think, okay, 2 times 4 could be equal to 8. Then I check 2 plus 4, does that equal 6? And that's the way we want to factor this, is 2 and 4. So those values that we just found, the ones written in red, I'm going to put as my constants in the factorization. I'm also going to bring down my x that I factored out at first. And notice that we've factored that polynomial. It's in linear terms now. So that's a good thing in terms of solution, because now all I have to do is set each individual term equal to 0. And that's using the zero product property. So the idea is if for instance, I just had a 0 here for x, it wouldn't matter what these values in these two parenthesis groups was, because 0 times anything is still 0. That's the zero product property. So we set the initial x equal to 0, and that's an immediate solution, so I'll circle it. Our second solution will come from this factor, so I'm going to set x plus 2 equal to 0. And then that's a smaller linear equation to solve, so I do want to subtract 2. And that gives me a second solution, x equals -2. And then our final solution comes from that third factor, x plus 4. Set that equal to 0, solve by subtracting 4 from each side, and we get our third solution, x equals -4. We can have as many solutions as there are the highest power in the equation. So if I have this degree of the equation is 3, I could have up to 3 solutions, and that's what I'm seeing here. I've got 3 actual solutions. The way to put that in a one kind of stop shop in terms of finding our solutions is the bracket notation. So x equals curly bracket. And then the traditional way to organize our solutions is from least to greatest. So -4, comma, -2, comma, 0. And that would be my final answer. Let's take a look at a second example that involves a degree 4 polynomial equation. Our second equation, notice, is already somewhat factored. I have on the left the quadratic x squared plus 2x plus 3. And then on the right, I have the quadratic x squared plus 6x plus 9. So what I want to start off is I want to see if I can factor either of those quadratics, and then if I can factor it, I'll use it to solve for those solutions. If I can't, I'll employ a different strategy. So let's in fact take a look at this second one. So I'm going to really look at this one that I'm highlighting in green, x squared plus 6x plus 9. And I'm looking there because I think I can factor that quadratic. So what I'll do is I'm going to bring my x factor, and we just use this. So remember, it's lining it up with ax squared plus bx plus c, that standard form of a quadratic. So I'm trying to multiply to my c term, which is 9, and add up to the b term, which in this case is, again, 6. So two numbers that multiply to 9, yet at the same time add to 6. So I can think, okay, 1 times 9 is 9. 1 plus 9 is 10. So that won't work. It's got to add to 6. So 9's a perfect square. 3 times 3 is 9. And eureka, 3 plus 3 is actually our 6. So that's going to give me two identical binomials. And I would factor this quadratic x squared plus 6x plus 9 as x plus 3. And again, those 3's are coming from that x factor times itself, x plus 3. Now, we'll finalize that one here because really I can use the same idea that we used in our last equation to use zero product property to come up with those solutions. And then we'll deal with that other quadratic in a moment. So let's set these guys equal to 0. And you can kind of see, because they're exactly the same, the solution should also be exactly the same. And I'll just subtract 3 from both sides. And yes, indeed, both of these yield the solution x equals -3. So we'll place that on the back burner. We've already come up with the solutions. I need to see what I can do with now this second quadratic. So that one, let's highlight it in the blue just so we can see it. So we're looking at x squared plus 2x plus 3. Let's try to set up the x factor for that one. So we're asking ourselves, what will multiply to the c term? So let me put the standard form ax squared plus bx plus c, because that's really how we're identifying how to solve these quadratics, by their coefficients. So I'm multiplying to 3 and adding those same two numbers up to get the b term, which is 2. So 3 only has two factors. It's a prime number, so it's 3 and 1. 3 times 1 is 3, that works. But 3 plus 1 is not 2. And because there's no other factors for 3, what I have to say is that this is unfactorable. It just doesn't factor with integer values or even rational values. So that's okay. What I need to do then is use a different strategy. So the second most traditional strategy to solve a quadratic is to use the quadratic formula. So let's remember what the quadratic formula says, and then we can use it to solve this second quadratic here in the turquoise. Quadratic formula says that x will equal a big fraction. So I'm going to set up the fraction line, and notice these are my a, my b, and my c from that standard form, ax squared plus bx plus c. So the way it goes is b squared. I get so excited I say it wrong. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. So lots of different letters there, but really there's just 3 of them, a, b, and c. And so when I go to solve by quadratic formula, that's what I want to do first, is say for my function, what's my a, my b, and my c? So I'm looking back at this quadratic. My a is 1, my b is positive 2, and my c is positive 3. So I just want to reset up the formula with those 3 coefficients plugged in. So I'll just put equals here. And the way I'm going to do is with parentheses. So negative parentheses, my b is 2, plus or minus the square root of b squared. So that's 2 squared. Those parentheses are important, especially when the b value is negative. So I make a habit of just writing them. Minus 4 is always there. 4 is part of the formula. A is 1 times c is 3 all over 2 times a, which again is 1. So the way quadratic formula goes is I now want to simplify it. So a lot of the simplification focuses right on the stuff that's under the radical. If you look, I've simplified the stuff that's outside of the square root. The stuff under the radical is important enough that we actually give it its own name. So I'm going to highlight it in yellow just so you can see what it is. It's this b squared minus 4ac, which for us is the numerical expression 2 squared minus 4 times 1 times 3. Let's name that part that I've highlighted in yellow. That's called the discriminant. And the name discriminant really, it's there to say whatever's there in terms of the number, once I simplify it, will tell me what kind of solution I've got. So if the discriminant is positive, the solution is going to be real. And it could be either rational or irrational. And in fact, we could have gotten our solutions -3, the ones that we got from our first quadratic using quadratic formula, and those would have been examples of rational, real solutions. Irrational ones are like if I get a prime number under that radical, it would be a decimal that never repeats, never ends. But that's when that discriminant is a positive number, once I've simplified that out. If it's a negative number, I can't algebraically take the square root of a negative number and give a simplified answer in the real numbers. I can in the imaginary numbers. And that's what I would say. If I get a negative discriminant, I would say that the solutions are going to be imaginary. Another name for imaginary, remember, is complex. Because imaginary numbers have 2 parts to them. So we'll see here what type of solutions we get. So we're right there at the moment to see that. So I'm going to put my square root, and then I just need to simplify. So 2 squared is 4, minus 4 times 1 is 4 times 3 is 12. 4 minus 12 is negative 8. And so as I look at that simplified discriminant, what I see is that it's negative. I'm going to have 2 imaginary or complex solutions. Well, let's find them. So I do want to simplify this square root of negative 8. And the way I'm going to do it is I'm going to look and see what are the pieces of negative 8, and I'm going to kind of factor them out. So I'm going to write this as negative 2 plus or minus the square root. And I'm going to split, first of all, split the negative off that number. So I'm going to put negative 1 separate from the 8. But then I also want to see, does 8 include any perfect squares as part of its factors? And remember, perfect squares are like 4. 4 is 2 times 2. 9 is 3 times 3. 16 is 4 times 4. 25 is 5 times 5. So I see that 8 has a factor of 4. And then I'm going to put the remainder 2. Now, that allows me to simplify this discriminant more and more and more. So let's create a little bit more room here. So what I'm going to do is I'm going to split it even further just so you can see it by step. So it's negative 2 plus or minus. I'm going to split these now into individual square roots. So it's the square root of negative 1 times the square root of 4 times the square root of 2. And I want to simplify these two. So the way that we defined complex or imaginary numbers in algebra 2 is that the square root of negative 1 equals the basis for the imaginary numbers, which is I. So my answer is going to look like negative 2 plus or minus I. And then square root of 4 is simply 2. And I'm going to put that 2 in front of the I. And then bring that piece that doesn't take the square root and just record it. And then to finalize, I'll put that denominator of 2. Now we can take it one step further in the simplifying. I can apply that, or really distribute that denominator of 2 to both of those terms. And so what that would give me is negative 2 over 2 plus or minus 2i square root of 2 over 2. And then I see cancellations. That's what we like. So that's 2 divided by 2 is 1. And I also see another 2 divided by 2. So what that leaves me with is negative 1 plus or minus I times the square root of 2. And you can see real clearly why we call imaginary numbers complex numbers. They have 2 parts. It's a complex arrangement. So the 2 parts here are the real part. So that left-hand number, notice that's a real number, negative 1. So that's the real component. And then the part that includes the I is the imaginary part, or the imaginary component. And that's why we call them complex, because they got 2 parts, a real part and an imaginary part. So definitely, like, quadratic formula is real useful because it reveals what sort of solutions any given quadratic has. So what I'm going to do is I'm going to record this in my solution set. So I just need to remember I had 2 solutions from earlier. So just to highlight those in this pink highlighter, that's negative 3. So I'm going to write it with the bracket notation, x equals, and then I'll put my imaginary solutions first. Now, one thing you can do is you can split it. So negative 1 plus I square root of 2, negative 1 minus I square root of 2. And that, again, that's equivalent to saying -1 plus or minus I squared of 2. And then I had a -3, but I had two of them. So what I'm going to say here is -3 multiplicity 2. So recall from our work finding real zeros of polynomial functions, whenever you've got a repeated factor, that represents a multiplicity, and your multiplicity is just how many of them do you have. Well, I had two factors of x plus 3 that gave me the two solutions -3, and that gives me multiplicity 2 for that solution. Well, thank you for joining for this investigation of solving polynomial equations. I'll let you go and solve your polynomial equations by factoring and using quadratic formula. See you soon.